Session 5, Confidence Intervals and Hypothesis Testing. In this session, I will be introducing the Stata command for constructing a confidence interval and testing a hypothesis for either a single sample or for two samples. I will also introduce more on the cross-tabulation or the two-way table, and I would like to talk about a different type of hypothesis testing, the chi-square test, for analyzing categorical data. So we'll be using a new data set for this session. The data set is from the American National Election Survey or Election Studies. So please load the Session 5 example. You'll see that 4 variables are included in this data set. And if you take a quick look at the labels here, basically in this data set, we collected information on respondents' age, respondents' gender. We also asked if the respondents have a health insurance and also self-evaluation on probably their health status. Also, if you open the data browser, you can take a look at age being the quantitative data. We also have 3 categorical data or qualitative data. However, since the text of the 3 data or of the 3 variables are already in blue instead of red, this means that all 3 variables are already encoded into a numerical form. So if you do a quick summary, you can see that age is a quantitative data that takes values from 18 to 90. Gender is a binary variable that takes a value from 0 to 1. Please notice that we do have some missing information for gender. The other 2 variables, we have some negative values here. Usually 99, negative 99, negative 9 are basically showing some missing response or refused response in a survey. Okay, so this means actually we do need some data cleaning work to be done. Okay, it looks like we're fine with the age, but in terms of the gender, we do want to look at whether female takes a value of 0 or 1 and how many observations are missing for this information. So the best way to do that is you can first tab gender to take a look at the 2 categories, and I recommend you to include the missing observation. So if you do tab gender missing, you will see that we have 1 category being female, another being male, and we have 38 missing observations. In the meanwhile, if you do this tab gender again, but in this time without showing the label, so tab gender missing and also no label, you can immediately associate which values are assigned to which category. So actually the variable name is better to be called male, because in our case, male is assigned to have a value of 1. Okay, but now I'm just going to drop the observations that are missing for gender. So I'm going to drop if gender is just missing, nothing. So click enter, 38 observations are deleted. Okay. Furthermore, I'm going to use the tab missing, tab no label to continue to study, learn, and deal with the other 2 categorical variables. Sometimes you may also have missing data for any other quantitative variables. So you also want to kind of examine whether these are the case. So now I'm going to tab my first variable on having insurance or not. So tab V161112 missing. I do not have any missing categories, but I do have 1 category that shows refused and another category that shows don't know. So actually I have 4 observations that does not give me the information on whether the respondents have an insurance. Okay? And also, I'd like to know how the numerical values assigned for these 4 categories. So I will do tab missing again with no label. So now I know that -9, -8 is associated with refuse, don't know, and I have 1 for yes, 2 for no. Now I'm going to drop if V616 equals to -9. If it's a refused response, I need to drop it. So 3 observations will be dropped. I will drop again if it's equals to -8. You can do it all together, just have like an if statement, if and or statement. So now I'm going to enter, and 1 more observation is deleted. Okay, it's probably also a better idea to rename the variable. So I'm going to rename this variable. That's called insurance. Okay, so now I'd like to deal with the health status variable. I'm going to do tab CV15 missing. Okay, so I have 5 categories. Okay, and also I have 2 respondents who refused with the answer. So I'm actually going to, if you'd like to see the no label version, you can do that, because sometimes the name of the categorical text just give you excellent, very good, good, fair, poor. You don't really know what are the numerical values assigned with each category. So if that's the case, you always want to do a no label to look at the actual numerical values assigned behind each categories. So now I know that I need to drop the -9. So drop if value equals to -9. Remember, after the if statement, we want the double equal sign, because we are kind of testing for that equality. If this equality is valid, we're going to drop. We're not defining some information. So if I drop, I will have 2 observations deleted. And I'd like to name this variable, rename to be, for example, health. Okay, so now if I sum all my variables again, I have some well-cleaned data set where I have 4,106 respondents or observations left. And insurance from 1 to 2, so it's a binary variable. Health is from 1 to 5, gender is 0 to 1, age is from 18 to 90. Of course, you can, if you'd like to have insurance 1 being yes and 0 being no, you can just quickly use the recode and just recode insurance 2 equals to 0. So it's going to be recode insurance. If you want to do 1 is 1, that's fine, because 1 is still going to be 1, but 2 is going to be 0. Okay? If you like to do that, that's fine, but I'm not going to do that because these are just categorical variables. I'll just leave it for the categorical variables in this case. Sometimes I do want kind of more binary variables where the values are either 0 or 1. If that's the case, I would like to recode. Okay, so this is the more cleaned version where I dealt with many of the things with my variable, and I also dropped many observations compared with the previous raw data. So it's actually always a good idea to just save another version. For example, I'm going to save it as session 5 example cleaned. So that you still have a version for your raw data and another version for your cleaned data. Okay, so to just summarize what I did, sometimes whenever we load a new data set, it's always better to do some cleaning and preparation, and definitely always get familiar with the variables and the data that you are working with. You want to look at how many variables you're working with, type of variables, and also if there's any missing observations, how you want to deal with the missing observations. Sometimes if it's not a primary variable you're going to examine, and it has a lot of missing information, instead of dropping those informations, you may consider not using that variable at all. So sometimes it's something to consider. Furthermore, you want to look at whether there's need to regroup or recode some of your values in the variables. You want to rename the variables for the convenience, and you want to save a new version. Okay, so in the next, I'm going to talk about the Stata comment for constructing a confidence interval. The comment is actually very simple, but if you recall the concept of confidence interval from the class, we're going to construct a confidence interval for age. This is the only quantitative data we have. So if I'm going to do a sum, suppose that we're trying to look at the information or understanding gender, age, and health, and insurance purchasing behavior for everyone in the US, then we collect a sample of around 4,000 respondents, right? Because in statistical inference, we need to care whether we're working with population or whether we're working with a sample. So now we have a sample. So if I'm going to sum age, my sample size is 4106, my sample mean is 49 something, and my sample standard deviation is 17.55. Okay, so using the traditional way to manually calculate a confidence interval, basically now we want to say construct a 95% confidence interval. If you recall, the critical value is 1.96, right? So I'm actually going to use Stata as a calculator to calculate the two bounds of my interval. So the lower bound would be the sample mean, which is x bar. I'm going to copy this number, copy, paste, minus 1.96 multiplied by the S and divided by the square root of n. So that's going to be 4106. Okay. So I'm going to click enter, and it calculated that the lower band of the interval is 48.99. Now I'm going to calculate the upper band, which I just need to change the minus sign into a plus sign. So I'm calculating x bar plus 1.96 multiplied by s divided by the square root of n. Click enter is 50.066. Okay, this is how we did in our regular lectures. But if we know the sample and we know the sample information, we can actually use a one-line comment to calculate this interval. And the comment is called CI, stands for confidence interval. CI means and the variable. You can calculate the confidence interval for a list of variables at the same time. Okay, so that's why I have a plural here. But let's calculate CI means age. That's it. If you click enter, by default, Stata will always choose an alpha of 5% or always choose 95% confidence interval. But as you see, we calculated correctly. The lower band was 48.99, the upper band is 50.066. Okay, so we do have some other options. So for example, if you'd like to construct the 90% confidence interval or the 99% confidence interval, you just need to give an option and override is 95% default. So the way you do that is just CI means age level 90. So you got the 90% confidence interval. If you calculate CI means age 99, you got the 99% confidence interval. Okay, so these are just very easy ways to calculate a confidence interval. If you're going to supposedly treat all of the variables as quantitative variables, you can calculate a list of variables at the same time. So I'm going to do, say, age, insurance, health, and gender. If I click OK, you can calculate. It will still give you the information on the mean and standard error. If you see here, standard error is a little bit different than the standard deviation from the sum. Standard error is the standard deviation divided by the square root of n. Okay, so that's basically mean plus and minus that standard error that gives you the interval. So you could calculate a list of variables at the same time. Okay. On the other hand, if our target parameter is, for example, population variance or population proportions, you could also use the same CI comments and to calculate, for example, the 95% confidence inference for a population variance. So for example, if I can calculate CI variance age. So now I calculated a different 95% confidence interval. This is based on that the sample variance is my sample statistics here. And I constructed a 95% confidence interval around my sample variance and hoping that my population variance is enclosed within this interval. Okay, so same thing for population proportion. And whenever we're calculating a population proportion, this is usually good for qualitative data. We do not have a mean or a variance or a standard deviation. Instead, we want to look at the percent of one category or a percent of one group among the population. For example, if we want to know if the population proportion for female gender is actually a binary variable, is a categorical variable, right? So you could actually calculate CI proportions gender. So it will calculate a 95% confidence interval for that population proportion, which is the percent of male in the US. So this is the confidence intervals. The next one we're going to talk about is the hypothesis testing. All the comments today are very simple. It's just a matter of fact on being able to read the Stata output. Okay, so suppose now we would like to test whether the age, so for example, the average age or the mean age of the whole US individuals, the average are, say, above 48, right? So now we want to test if the true mean age is above 48. So actually my null hypothesis is gonna be mu equals to 48, and my alternative hypothesis is going to be mu greater than 48. Okay. However, when it comes to using Stata for hypothesis testing, we don't really need to care about whether we're doing an upper-tailed test, a two-tailed test, or a lower-tailed test. The comment is exactly the same. Basically, you just need to do t test age equals to 48. 48 is the claimed value under H0. So you always just test whether age is 48 to see whether Stata can reject that null hypothesis. Stata will always do the 3 tests altogether after these comments. Okay, And the code is always going to be a t-test, even though for a large sample, we always said that it's going to be a z-statistic using a critical value from the z table. But Stata will accommodate that for either large sample or small sample because the t-statistic will converge to z for large sample. So the comment is always called t-test. So if you click enter, we're going to take a look at the result. Okay, so first of all, Stata will still, even though you're performing a hypothesis testing, Stata will still report several important summary statistics for you, including the 95% confidence interval. So it gives you the observation, the sample mean, the sample standard deviation, which is this one, and the sample standard error, which is the sample standard deviation divided by the square root of n. And it will give you the 95% confidence interval. At the same time, Stata will show what is your non-hypothesis. And no matter what type of test you want, Stata will report all three tests for you. It will always do a two-tailed test listed in the middle. So the alternative hypothesis is that this mean age is not equals to 48, okay? And it will also give you the alternative where the mean is less lower-tailed test, and then when the mean is higher, the upper-tailed test. So you don't really need to worry on specifying your alternative hypothesis in the Stata comment, okay? So let's try to recall our traditional critical value method, where, for example, if we want to do, let's probably do a two-tailed test because the critical value was just 1.96, which we just used before. And the t statistic is something we need to calculate. So we need to find t or z for large sample, right? So let's quickly use Stata as a calculator to see if we find the correct test statistic. So display, I have to have x bar, which is 48. So x bar 48 minus mu 0, which is the value under h naught, divided by the standard deviation divided by the square root of n, 4106. Now I'm going to click enter. I have a z statistic or t, Stata does not distinguish here. That is 5.5789, which is always reported here. Okay, and it also reports the degree of freedom. However, it will still already converge to z statistic. Okay, so according to the traditional method, since t statistic is greater equals to 5.58 greater than 1.96, being the critical value, we reject h naught at 5% significant level. Okay. Remember, this is what we did in the regular lecture. However, in empirical research and especially in Stata, the most way we look at is through the p-value method because we do not have to specify a significance level. So therefore, using the p-value method, you could just say, since the p-value is equals to 0.0000, so we can reject h naught at 1%, 5%, and 10% significant level. Right. So in a non-technical way of interpreting this is that the true mean age for US residents, suppose, is different from 48. If it's a one-tailed test, we'll say it's greater than 48. For the one-tailed test, we can also reject at the 1%, 5%, and 10% level. So if your research claim is about a one-tailed test, you can say that the true mean age for US residents is greater than 48. Okay. So this is just the one-line comments for a hypothesis testing for one single sample. Again, it will create this 95% confidence interval for you. So sometimes we do not even need to use the CI means comment. You could directly always use the t-test, and it has everything for you. Okay. Of course, if you do the t-test age equals to 48 with a comma showing a level of 90%. Okay. So your hypothesis testing will not change or be affected by this option at all. You see the t-statistic still the same, the p-values are still the same. The only thing that's affected is that it will override the 95% confidence interval and show a 90% confidence interval for you. So this option is always for the confidence interval. Okay. So the next one, let's look at the hypothesis testing for two samples. So for two samples, usually our research question is always to look at whether the mean is different across two different groups. Therefore, the non-hypothesis is always that the difference is 0. And of course, the alternative hypothesis could be the case where it's not 0, it's bigger than 0, or it's less than 0. So in that case, whenever we do an hypothesis testing for two samples, we do not have to give and claim the value. We do not have to say test this variable equal to something. Alternatively, we want to test this variable across some group. And at least by a bi-variable, this is saying that because we are testing for two groups, we have to always have a binary variables included in the parentheses. Okay, so for example, now we would like to test the average mean, so t-test age across insurance. So we want to look at whether the mean age for US residents, whether they are different for those who have insurance and for those who does not have an insurance. Okay, so if I click enter, you will see a test results here. So first of all, it will still show you some basic descriptive statistic for all the values where for the group where insurance is 1 and for the other group where the insurance is 0. It also calculates the difference for you. Okay, so more or less, if you see that the mean age for those who have insurance is about 50 something, and the mean age for those who does not have an insurance is about 40 something. So probably it's really a big difference on the mean age between the two groups, right? So this is our non-hypothesis, and if you'd like to look at only a two-tailed test, by looking at the p-values here, it's pretty slow, it's just 0. This means that you can reject the non-hypothesis at 1%, 5%, and 10% significant value. The mean age across those who has insurance or who does not have insurance are statistically and significantly different. Okay, and at the same time, we also know that the true difference value, the true difference is actually from 8 to 12 something. So the true difference is a positive value. Therefore, we know that the mean age for those who has an insurance is statistically greater than those of the mean age without an insurance. Okay, So make sure that you still intuitively understand the hypothesis testing for a single sample or for two samples. Be able to still understand the critical value method or even the confidence interval method, and also be able to read the p-value to quickly make rejection decision at any significant value. Okay, so I can probably also test age across gender. So by gender. Gender is another binary variable. So if I'm testing the mean age across female and male, I can do this comment. So if I click enter and I quickly read my p-values, it's 0.5, 50%. So it's a very big value. Therefore, I fail to reject my hypothesis at 1%, 5%, and 10% significant value, right? So in the US, there's no difference on the mean age between females and males, okay? So again, it's very important to notice that we do have to have a binary variable in the parentheses. For example, we have health, which takes a value from 1 to 5 categories. So if you want to test the age across different self-evaluated health status, you're going to get an error message, so health. If you click enter, you're going to see an error message, more than 2 groups found, only 2 allowed, right? So if you still want to test that, you need to find a way to regroup your health status and to create a binary variable, right? So for example, if I'm going to tab health. So I have excellent, very good, good, fair, and poor. So probably I can generate a new variable that's called good health equals to health. And I'm going to recode this good health variable so that 1 to 3 is good. So I can do from 1 to 3 being 1 and from 4 to 5 being 2 or being 0. It's really up to you as long as it's a binary variable, right? Sometimes if you forgot about the from and to, if it's not too many categories, you can always do 1 equals to 1, 2 equals to 1, 3 good, that's 1, and then 4 being 0, 5 being 0. That's the same thing, okay? So if you click enter and double check that you created a new variable that's called good health, and it only takes a value of 0 and 1, 1 being good health, 0 being not good health, fair or poor. So now you can test the mean age across respondents with different health conditions. So by good health. And if you test that hypothesis, right? So the mean age for those who does not evaluate themselves with a good health is around 45, and the other group is around 48, right? So 54 and 48. So the p-value is actually 0. This means that the mean age is statistically and significantly different across the two groups, good health and no good health. Okay. So hypothesis testing for 2 samples. Now I would like to talk a little bit more on the cross-tabulation, also called a two-way table or a contingency table. Basically, if you recall from previously, we talked about this tab comment. I also used this comment many times today. So if we can tab a categorical variable, we'll see some frequency tables. So the tab variable missing option, and also sometimes if we tab the variable, we can quickly generate new binary variables for each category. Okay. So we could also use this tab comment to create a two-way table. So basically, for example, if we tab, for example, insurance, gender, So we immediately see a two-way table and the number of observations over the total, and what a proportion of respondents having insurance being female or having insurance being male. We can easily to compare that, right? Actually, another option for this two-way table is you can show the percentage either crossing the row or either crossing the column, right? So for example, if you do tab insurance gender, comma, row, it will show you the percent according to the row. So the row will give you 100%. So this is to show you that among those who have insurance or who said yes for having insurance, 53.33% are female, 46 are male. And among those who said no, 48% female and 51% male. Right? Alternatively, you can also tab insurance gender column. You can do column or just col. Okay? And now it will have this 100 on the columns. This is to show that among female respondents, 91% of them have insurance and 8% does not. Among all the males, 90% have insurance and 9% do not. Okay? These are two additional options for you after the tab for creating a two-way table. More importantly, I'd like to introduce another type of hypothesis testing, which was not covered in the regular lecture. So sometimes we do want to do some categorical data analysis. Instead of asking if there's any differences in the mean age of quantitative data across different groups, sometimes we may just want to know the difference between two groups across other groups, right? So for example, a research question could be, I want to know if there's any difference between male and female, or in the percentage of male and female who favor the climate change adaptation program. So I would actually be examining two categorical variables. One is the gender, which is male and female 0 or 1. Another one is going to be my row variable, that is favor or oppose. Okay? So then our non-hypothesis is to say that there's no statistically significant difference in the percentage of men and women who favor the climate change adaptation program. And the hypothesis testing that we're going to do is called a chi-square test. The symbol is called a chi-square. Okay? Although this is a different type of hypothesis testing, but the key steps or the methods for hypothesis testing are exactly the same. You could do a critical value method, which is to calculate a chi-square statistic. Okay? Remember, we are examining categorical variables. Therefore, those variables will not have a normal distribution. Instead, they have a chi-square distribution, which I will not talk in depth. But because it has a chi-square distribution, we're going to calculate a test statistic that is called a chi-square statistic. Okay? And then we're going to find the critical value from the chi-square table. By comparing the chi-square statistic and the critical value, then we can look at the rejection decision, look at the rejection region, and state the conclusion. So exactly same idea for any hypothesis testing. Alternatively, and also very commonly used in empirical research, is we'll just let Stata to do the test and report the p-value. We're going to find the p-value from the Stata output, and then for any given significance level, we can state our conclusion. Okay, so the Stata comment for chi-square test is you're still going to tab the two categorical variables you are interested to. But other than just looking at and comparing the percent of different group in different categories, we can perform a chi-square test at the same time, which just to additionally give comma CHI. So for example, right now I'm going to do, I want to look at, for example, female and male who are, whether there's a gender difference in terms of purchasing insurance. So probably I'd like to do gender on the vertical row and then insurance on the row. One on the column and one on the row. So the option is going to be CHI. Okay, so if I click enter, I'm still gonna see this frequency table or two-way table. Alternatively, Stata will in addition produce this chi-square statistics for you and the p-value. So in this case, we have a p-value which is 0.06. Okay, so it's 6%. This is to say that we can reject the null hypothesis at 10%, but we cannot reject the null hypothesis at 1% or 5%, right? Remember, how do you read the p-value? So we could do another test to, for example, look at insurance and health. So let's first look at insurance and good health. So we want to look at whether the percentage of respondents purchasing or not purchasing insurance, if it makes a difference for having the good health or not. Okay, so I'm going to click enter. I have a very big p-value as expected, right? So actually, for those, if you can still do the option, for example, row. So for those who purchased the insurance, 80% of them self-evaluated to have a good health. And for those who do not have an insurance, only 72% indicated a good health. So actually purchasing insurance or not does matter for those who indicated good or not good health. It's statistically significant at 1%, 5%, and 10% significant level. Okay, so the cross tabulation and the chi-square test does not have to be only binary variables. As long as these are categorical variables, it will be fine. You could have more than 2 categories. For example, we could do tab insurance and health. We have 5 health status. So I'm going to click enter. We could still produce this two-way table, and we could still have a chi-square test, and the p-value is still small and statistically significant at 1%, 5%, and 10% significant value. Okay. So these are all the hypothesis testing we'll be using for this class. Hopefully this session will help you review some of the concepts we learned and also help you to conduct any of these tests for your empirical research.